This video presents part 2 of the probability review. To facilitate this review, we'll use the simple data set that you're looking at here. So let's take a second and make sure you understand well what it represents. In the columns, we have information about whether a person does or does not have a disease. D plus stands for disease positive. These are people who have the disease. D minus stands for disease negative. These are people who do not have the disease. The disease goes unnamed because it's just a classroom example here. The total gives you the total number of people in the data set. Now let's take a look at the rows. The rows contain information about how a diagnostic test turned out. T plus is test positive. T minus is test negative. And then the total is again the total number of people in the data set. So we have the intersections of rows and columns which enable us to parse the information a bit more precisely. So for example, the number 95 appears in the test positive and disease positive rows and columns. So that means 95 people who had the disease tested positive for the disease. Look below that to the 5. 5 people who had the disease tested negative. If we move over to the next column, 99 people who were disease negative tested positive for the disease. And 9,801 people who were disease negative tested negative for the disease. The totals are as shown. 194 total people tested positive, 9,806 tested negative. 100 people have the disease, 9,900 people do not have the disease, and there is a total of 10,000 people in the data set. So with that behind us now, let's introduce our very first concept here, which is the marginal probability. That's the probability of a single event. The syntax for this would be capital P stands for the probability of, and then in parenthesis you would have the event that you're talking about. So A stands for anything. So the probability of A is shown there is the syntax for the probability of a single event. I've given you a couple examples of single events. What's the probability that a person chosen at random from this group of 10,000 is disease positive? Well, there are 100 people who have the disease, and that's 100 out of 10,000, or 0.01. The probability that a person tests negative is 9,806 out of 10,000, or 0.9806. So marginal probabilities are probabilities of single events. These probabilities, of course, must be a value between 0 and 1. The first rule to make sure you know is the complementarity rule. The complement of an event is all outcomes that are not that event. So I've given you an example here. The event is the probability that a randomly selected person is disease negative. And that probability, looking at the table now, you can see the total number of disease negative in the bottom row, 9,900 out of 10,000. So that gives us a probability of disease negative of 0.99. The complement to that would be everybody who's not disease negative. So notice the syntax here. The probability of D minus and the apostrophe there, or a stroke that basically means not disease negative. So that would be all outcomes that are not the event of interest. In this very simple table, we only have 2 outcomes. But if we were looking at the throw of 2 dice, we could have 36 outcomes. So the complement can comprise many events. In this case, however, it's 1 minus 0.99 or 0.01. You could derive that by identifying all the outcomes that are not the event. In this case, disease positive is 100 out of 10,000, and that would get you the same answer. But the simplest way to estimate the probability complement is to take 1 minus the event whose complement you seek. Okay, so this is making that point made earlier that something has to happen, that the sum of all the probabilities of all the possible outcomes for your event have to equal 1. We can exploit that property in this complementarity rule. In risk assessment, it would not be unusual to be interested in the probability of 2 or more events. To keep this review simple, we'll focus on 2 events. And let's begin with the generic events A and B. You would apply the general rule of addition to estimate the probability that both events would occur. Here's how the syntax works. By the way, I have an unfortunate choice of bullets here. You notice that the first bullet is a blue dot, the second bullet is a dash. So please do not think that is a negative sign. I'm sorry for that outcome, but just remember that the first symbol there is a bullet and not an arithmetic sign. So our syntax is probability that event A or B occur, and it is equal to the probability of A plus the probability of B, and from that sum you must subtract the probability of A and B. Now I've translated A and B into symbols that would be relevant for the table that we're looking at here. So we're going to examine the probability that a person chosen from at random is either disease positive or they test positive for the disease. And you can see there the substitution of D plus for the A and T plus for the B. Our next job then is to calculate these values. So the probability that a person has the disease, that's 100 out of 10,000 people. And you see that there's the first fraction. To that, we add the probability that the person tests positive for the disease. That's 194 people out of 10,000. But notice that that 194 people is equal to 99 people without the disease and 95 with the disease. Also notice that when we counted the number of people with the disease, we counted the 95 that tested positive and 5 that tested negative. So that value there, the 95, it got counted twice. And in our syntax here, this would be an example of being disease positive and test positive. So that last term in our rule there, the probability of D plus and T plus, that's basically saying when you have a table, and the table makes it easier for us to grasp these consequences, when you have a table, we're looking for the intersection of D plus and T plus. That's 95 people. 95 people out of 10,000 were counted twice. So in that very last row, we have the calculation. 100 people plus 194 people less the 95 people that were counted twice gives us 199 people out of 10,000 for the probability that you see there of 0.0199. So this is an application of the general rule of addition, and what it's saying is the probability that a person selected at random from these 10,000 people will be either disease positive or will have tested positive for the disease is almost 2%, just as shown. In the last slide, we applied the general rule of addition. And the results of that are repeated here in the very first bullet. This time you see them in decimal form. The probability that a person is disease positive or they test positive for the disease is 0.0199, almost 2%. Notice disease positive and test positive have a cell in common. 95 people are both disease positive and test positive, and that is the element that needs to be subtracted out. That is the probability of disease positive and test positive. We're going to call that a joint probability because both conditions occur at the same time, or both conditions occur jointly. Now, by contrast, let's take a look at a different application of the addition rule. This time we're looking at the probability that a person is disease positive or disease negative. Using our table, the probability that a person is disease positive is 100 out of 10,000, or 0.01. And the probability they're disease negative is actually the complement to that. But using the table, it's 9,900 out of 10,000 people, or 0.99. Now, what is the intersection between those two events? How many people are both disease positive and disease negative? And the answer is none. In our table, these are both column events, as opposed to the previous example that had one column event and one row event. When you have mutually exclusive events, the probability that both things occur at the same time is 0. So let's continue to the next slide for the takeaway for that. I have a confession to make. The first time I was taught probability, I didn't learn it very well. I didn't learn it very well the second time either. It took me quite a few tries to finally get the concepts and principles here. And I tell you that for this reason. If you happen to have an old statistics book or an old probability text and you go to the index and you look up addition rules, there's a good chance that there will be multiple locations in your textbook and that you'll see different formulas in different places. The general rule for addition is, as we saw a couple of slides ago, the probability of A plus the probability of B minus the probability of A and B. However, for mutually exclusive events, as we just saw with disease positive and disease negative people, that joint probability of A and B is 0. When the joint probability is 0, that term, probability A and B, is sometimes left out of the formula. So if you go to your book, you might see two different formulas and you may be confused. You are safer if you use the general rule for addition because the term is always in there, and then all you have to do is remember that it's okay that there will be times when it is 0, such as the example we just had. The probability of disease positive and disease negative is 0. But for events that are not mutually exclusive, this joint probability of A and B can be a non-zero and positive value. And so in those cases, it needs to be subtracted from the sum of the two events that you're interested in. Now, I will offer one final word on this particular rule, and that is there is a general addition rule for more than 2 events. You can find a general addition rule for 3, 4, or 5 events, and it works essentially the same, which means you're taking the sum of all the individual events, but you must subtract out every instance where any part of those probabilities is counted more than once. So you can find that formula easily on the internet, on the World Wide Web, or probably even in a little bit more advanced textbook. Now we want to turn our attention to the multiplication rules of probability. How and when do you multiply probabilities? Here it's important to distinguish whether the events that we're interested in are independent or dependent events. When A and B are independent of one another, in other words, when the probability of A is in no way affected by whether B happens or not, and vice versa, then you have independent events. We are now looking at those joint probabilities, the probability of A and B. Notice the language is a little confusing. When we were talking about addition, we said the probability of A or B. Now we're talking about multiplication, and we're talking about the probability of A and B. So if you find yourself feeling confused, you're probably pretty normal. But this is why probability is not terribly intuitive, and you can't trust your gut. You have to know. So the probability of A and B, when A and B are independent events, is just the product of the probability of A times the probability of B. Recall that aquatic nuisance species probability that we looked at. There we had 5 events, a sequence of 5 events that was necessary in order for an aquatic nuisance species to become established. There had to be a pathway. The nuisance species had to arrive at the pathway. It had to survive passage through the pathway. It had to colonize on the other side, and then it had to spread from its colony. To estimate that probability of establishment, then, you would simply multiply these 5 events, all of which were independent of one another because they were conditional probabilities. And that's a concept that we haven't come upon yet. So we'll return to that before we leave this little mini lecture. What happens if A and B are not independent events? What happens if the probability of A is affected by the probability of B, or vice versa? In that case, the probability, the joint probability that A and B occur together depends on the nature of the dependency. That is usually in the realm of the world of physics. How does one occurrence affect another occurrence? When we're dealing with dependent events like this, the general rule of multiplication applies. So there is no nice, neat way to do it like you have for independent events. We have what appears in the next bullet. Here's how you read that. The probability that A and B occur together is equal to the probability of A times the probability of B, given that A has happened or is sure to happen. So that second right-hand term is a conditional probability. It's the probability of A times the probability of B, conditional on the fact that A has occurred or will surely occur. Risk assessment involves a lot of dependent relationships. Let's take a simple example. The aquatic nuisance species works as a decent example for independent events. But in the table we're working with, there are no independent events. Certainly, if you have the disease, we would expect that to affect the probability of testing positive for the disease or not. Likewise, not having the disease would affect the probability that you test positive or not. We could flip that as well. The probability that you test positive, that is affected by whether you have the disease or not. People who have the disease have a higher probability of testing positive than people who don't. So in this table, we have dependent events. All the events here are dependent. And what we do then is we need to apply the rule. Now I've translated it from A and B to disease positive and test positive. And with a table, these formulas are deceptively easy to work. Most of the time when you're doing risk assessment, you will not have a neat table in front of you, and that makes these calculations a bit harder to do. But let's look at our calculation here. The probability that a person is disease positive and test positive is equal to the probability that they're disease positive, and that is 100 out of 10,000 people. So that becomes our very first factor, 0.01. That is going to be multiplied by the probability that a person tests positive given that they are disease positive. So this is a conditional probability. We will consider them very shortly here, but let's talk about how this works. In the syntax, you see that vertical line that separates test positive and disease positive. What this basically means is we're interested in the probability of that first thing, testing positive. That vertical line, you read it this way, given that, and then the information to the right of it is information that we can depend on. So we are being told that the person is disease positive. Given that they're disease positive, what's the probability that they test positive for the disease? Now let's look at the table. Initially, we were concerned with 10,000 people. As soon as I look at that conditional probability and see that we are given the fact that this person is disease positive, we are now only interested in the 100 people who are disease positive. The other 9,900 have been excluded from this. So given that you are disease positive, what's the probability that you test positive? 95 people test positive, but it's no longer 95 out of 10,000. It's 95 out of 100, and that's 0.95. That becomes the second number. When we multiply them both together, we obtain the product 0.0095. That is the probability that a person will have the disease and test positive, both things occurring at once. Let's reconsider dependence and independence, looking at an event tree such as we have here. This is a picture of our table, and you'll notice that I began with the first node. Circles are called nodes. The lines coming from a circle are branches. Triangles are endpoints. So I began the first node asking the question, does the person have the disease or not? You'll notice the probability of disease is 1%. The probability of no disease is 99%. But here's what I want you to see. Take a look at the probability of testing positive. They vary. On the top branch, it's a 95% chance. On the bottom branch, there's a 1% chance. So the probability of testing positive is not constant. It depends. What does it depend on? It depends on whether the person has the disease or not. So if the test result was independent of disease, the probability of testing positive would be the same on both of these nodes and branches. Okay? So if you're going to be building even simple models like the one that we're looking at, it requires you to understand these rules of probability. Let's consider the notion of conditional probabilities. Conditional probabilities are based on a very simple but very important idea. information can change probabilities. Let me ask you a question I like to ask when we're in a face-to-face class. What's the probability that you're going to die today? That's kind of a rude, startling question, but we would like to think that that probability is relatively small. Maybe there's one chance in 100,000 that you'll die today. Let's use that number as a made-up number since we are not face-to-face. Now, I'm going to give you some information. Suppose you leave your building and you are hit by an 18-wheeler, a tractor and a trailer, and this tractor and trailer are going 60 miles an hour. So that's the information I'm giving you. Suppose that event happens. And now if I ask you, what's the probability that you will die today? I'm thinking that even though it's the same event, you are going to have a different probability now. It's going to be much higher. There may be a 0.99 chance that you'll die given that you get hit by an 18-wheeler going 60 miles an hour. And so that's the point. Once we get information, that can change the probability of a specific event. In this case, the probability that you would die today. So let's look at bullet 2. The syntax, once again, works like this. Probability that A happens given that B has happened or it is going to happen for sure. So the probability that A given B is not going to be the same as the probability of A if A and B depend on one another. So let's take this language that is so confusing and put it back in terms of the example I just gave you. The probability that you die today, given that you get hit by that truck going 60 miles an hour, is not the same as the probability that you die today if you dying and getting hit by a truck are dependent events, which they surely are. Okay? I know this is not easy, but it's important if you're going to be doing risk assessment to become familiar with these concepts. So if they give you some trouble, just keep working at it. You'll get there. Here is the formula. Bullet 3 gives us the formula for calculating this conditional probability. The probability of A given B is equal to the joint probability of A and B divided by the probability of B. Let's go back to our convenient and familiar table, and we're going to consider this conditional probability. Keep in mind, information can change probabilities, and the probability of A given B is not the same as the probability of A if A and B are dependent on one another. The third bullet repeats the formula that we just looked at. And in the fourth bullet, we're going to calculate a conditional probability, but we're going to do it using the table, and then I'll explain how you would do it using the formula. But let's use the table first, just so you can get the idea here. As a matter of fact, look at the very last bullet. The probability that you test positive, that's 194 people out of 10,000. 0.0194. That's the probability that you test positive. Less than 2% of the people are going to test positive. But let me give you some information, and then we'll revisit that probability of testing positive. The information I want you to have is the person is disease positive. So that's saying we're no longer looking at the entire table. We're only looking at those 100 people in the disease positive column. Of those 100 people, how many test positive? 95 out of 100 do. So the probability of testing positive has increased to 95% from that's slightly less than 2%. And these are the numbers that we had on the event tree just a couple of slides ago. So this notion that information can change probabilities is a powerful notion. So here's an important point to draw from what we've been talking about recently. When we're doing risk assessment, there are a lot of data gaps, so we often lack data. Still, we have to estimate probabilities. So absent empirical data to estimate probabilities, we frequently have to rely on subjective probabilities. That strength of belief idea. Subjectivists, they insist that rational belief is governed by the laws of probability, so they lean very heavily on these conditional probabilities in their theories of evidence and their models of empirical learning. Bayes' theorem is a simple mathematical formula that's used for calculating conditional probabilities. And I might add, parenthetically, that many people find its power and its beauty hard to grasp. So if you are one of these people, there's nothing at all wrong with you. This is just not intuitive information. To work our way up to Bayes' theorem, let me pose a question. You recall that the probability that a person who tests positive, given that they're disease positive, is 0.95. But let's suppose that the information that we start with is that the test is positive. Then what's the probability that the person is disease positive? That is, what is the probability of disease positive given test positive? Notice that this flips that conditional probability. It takes the two terms and reverses their order. This is trivially easy to calculate with the table, so that if you have tables prepared for you for all your risk assessments, probability calculations can be quite simple. The probability that you're disease positive given that you're test positive. Looking at the table, we have information that says this person is test positive, so I know only to look at that row. We have eliminated most of the people. We're no longer looking at 10,000 people. We're looking at 194 people. Of those 194 people, how many of them are disease positive? And the answer is 95. So that probability of disease positive given test positive is 95 out of 194. That's less than 50%. That's about a 0.489. So the interesting thing is people who test positive for disease more often than not don't have the disease. A couple of slides ago, I presented a formula for calculating a conditional probability. Here we have a conditional probability again, but the formula is different. It's a simple mathematical manipulation that we're not going to bother with here in our review, but it yields this very powerful and very useful Bayes' theorem. So the probability that A happens given that B happens is equal to the probability of A times the probability of B given A, and that product is divided by the probability of B. Beneath this, I have translated this into the terms used in our table. So I leave to you the exercise of going back and figuring out those three probabilities on the right-hand side of the equal sign. plug them in, and verify that you get the same answer that we just obtained. So here's the solution, and shame on you if you didn't work this problem out on your own. Using the formula at the top, translated from Bayes' theorem, we can flip the probability. This is what you would do if you did not have a table. You would have to have an estimate of the probability of being disease positive. And here we know that's 100 out of 10,000. You would have to have a probability of that conditional probability. Test positive given disease positive. And that's 95 out of 100. You would multiply those together and then divide that by the probability of a positive test. 194 out of the total of 10,000. If you do all the numerical calculations, then you should obtain the very same probability we had before, 95 out of 194, which is that 0.489, I believe it was. Yes, 0.489 is the probability. In this slide, I present you with two different event trees that enable you to see how the probabilities can be flipped. The first event tree on the left begins with disease and proceeds to the test result. The second event tree on the right begins with the test result and proceeds to the disease. All the same data, all the same table, it's just a matter of how you present it and how you package it. But Bayes' theorem helps us to answer some useful questions and to mine information from conditional probabilities to provide us with useful information for our risk assessments. Later on, when we get to quantitative risk assessment and we start talking about model building and things, we're going to talk about event trees, and we're going to say sometimes there is a chronological component, a logical component to an event tree, where you know what the first event has to be and you know what the second event has to be, and so on. Other times, such as in the present case that we're looking at here, it's rather arbitrary whether we begin with disease or the test result. Either one works perfectly well. So try to keep that in mind, and we will be spending a good bit more time with these rules and probability rules and event trees in subsequent courses in the program. You're going to need to know the laws of probability so that you can construct rational models when you are assessing risks. I have not reviewed the mathematical symbols that are often used, so if any of these that you're looking at are foreign and not at all familiar to you, it may be worth a little time brushing up on the symbols, and doing that through some of the videos at the Khan Academy may be the best way to do that. Let's review a couple of ideas from these two probability review videos. First, probability is a human construct. It's a number between 0 and 1. Probability estimates can be analytical, they can be frequencies that we observe, or they could be subjective judgments. There are laws that govern probability calculations, but the philosophies behind those laws may differ substantially. Probability is the language of natural variability and knowledge uncertainty. You need to have people who know probability to do good risk analysis.